start recording, even though there's nothing on the screen yet. We won't need the screen for a bit. And my voice is still recovering, so I don't really want to have to shout too much. So today we're going to talk about the last data structure that for the semester, graphs. And graphs are really kind of awesome because they talk about what humans care about, which are relationships. And the other big thing about graphs is that I'm not going to actually implement graphs at any point. I'm not actually going to, unlike all the other data structures which I've written from scratch, I am not actually going to write these things from scratch because it's tedious, for one, and the second is because there's so many better options. Now, in fact, today's the homework this week is going to be you learning how to use your IDE to use a library that was already created by someone else. So you're going to learn how to use essentially an external library. Now, as part of this also, and because of this, I actually will give you a small option from the last couple of assignments, which is that you can use a programming language other than Java if you so desire. You can do it in Python, you can do it in C, you can do it in some other weird language that you've been playing around with. I'm going to be doing anything I do in Java, but if you want to, for all the assignments that concern graphs, you can do it in any programming language you want. Okay, so long as I can, and if it's something esoteric like NIM, just make sure that I can just point me to a compiler. Okay, so NIM is actually great. It's like this really concise code that compiles straight to C, which is fantastic. So that's really nice. So graphs are a really abstract data structure because they talk about really abstract things. Now, I think at this point though that the discussion of graphs has really changed because graphs used to be about like the typical, the archetypical graph example, like what you do with graphs is that you you should look at my avatar on Canvas. It's actually a screenshot of this, and just look at this guy's face. He's like, I'm the wrong class. So, I
forget what artist did that picture.
It was a Golden Age Danish artist.
Yeah.
And for some reason, his name escapes me right now too, because I'm not an art historian.
No. And basically like that.
Yeah. So, so graphs, basically, the archetypical example for graphs is essentially talking about distances between locations or cost between locations. Like, say you're, say you've got, you've got Philadelphia over here, right? And you've got, Pittsburgh over here, right? And the relationship here, if we're talking about like cost, okay, is like maybe it's like what $46 now these days to drive from here to on the expressway, or we could talk about it in distance, right? We could describe a relationship, 320 miles, or we could just simply say there exists a relationship between Philadelphia and Pittsburgh, right? Okay, right. So graphs are really abstract. What you use them for is your decision, right? And depends on the certain application. The most common thing, though, the most common application used to be you can fly from city A to city B, and then from city B you can fly to city C, right? And then from city C you could also fly to A, right? There's routes between them, okay? But these days it's actually more useful. The big one these days is actually social networks and relationships between people. Like, for instance, this describes like some state on Facebook or something like that. A is friends with B, right? And B is friends with C, but A and C are not friends, right? So A and B are friends, B and C are friends, A and C have a mutual friend in B, but they're not themselves friends, right? Okay. That's one way we can look at these things. You can model graphs. Another way is you can model them like the Twitter subscribe model, right? Which is that relationships can be one directional or bidirectional. Okay. These are called directed graphs now. If we add arrows like this, A subscribes to B, and C subscribes to B, right? Because maybe B is a celebrity, okay? And they don't, and you know, so this guy has lots of followers, and you know, you don't necessarily have that many followers. Or maybe B and C are both celebrities, so A subscribes to both of them, okay? And because B is a bigger celebrity, C will subscribe to that. Or maybe, you know, this is, you know, so so basically these relationships are, you know, one way. They could also be that B and C also subscribe to each other, so you can have a two-way relationship there. So we're essentially having, we're going to put essentially two types of terms of graphs we're dealing with here. We're dealing with either a directed graph, which is with the arrows, meaning that relationships can be one way. So these could be one-way relationships, or if this is like distance, you could be describing that there's a one-way street that connects A and B, and then there's a one-way street that connects A and C, and then there's a two-way street that connects B and C, right? So you can go from B to C, you can go to C to D. This is what we call a directed graph, okay? So that's one kind of question you can ask about graphs. Are graphs directed or are they not directed, right? If they're not directed, they don't have arrows, and you just assume that everything's a two-way relationship. And that's kind of the default state of being for a graph. That the default option for a graph is that relationships between things are two ways. And then the other thing we ask about graphs is whether or not they're weighted graphs. In other words, do these have a number, right, applied to them? And they didn't for like a Facebook relationship, right? That you're just friends or you're not. But if these are like, you know, costs of flying to cities, to get from city A to city B might cost $120. B to C might cost $70, and A to C is 500, right? And so if you're trying to get to A to C, you're trying to figure out what's the cheapest way to get there. You're going to go, oh, well, fly to A to B, right? Take that 3-hour layover and go from B to C, right? So there's a, so, you know, and that's the type of problem that graphs deal with. One big problem that we'll be looking at is the shortest distance problem. Basically calculating the shortest distance from between two things on a graph, two nodes on a graph, as we call them. Okay. So what are graphs? Well, I've been drawing them, and graphs are defined basically by they're defined as a set. Mathematically, we say that a graph is a set of vertices and edges. That's the mathematical formulation for this. If we needed to do more math, and this is important because the only reason, because you're going to just see this notation later, which is, you know, which simply says this with a magnitude of V. What's the magnitude of V? What's the magnitude of the set? That's how many things are in the set. So we're saying, if you see this symbol, this says this is the number of vertices, and this is the number of edges. So what are the vertices and edges? Well, vertices are things. Like literally, they're anything you want them to be. They're all kind of the same thing, right? So a vertice, those are like the points we see. You know, the A's, the B's, right, and so on and so forth. And your edges are the relationship between them. We represent them as lines drawn between objects. Now, for edges, they have to be associated with vertices. An edge just can't exist on its own like this, right? So you have your vertices, and then you have your edges, which connect those vertices together. So vertices are the things, and the edges are the relationships between things. You can have an empty set of vertices, which means there's just no things. And you can also have an empty set of edges, which means if there's a bunch of things, there's no relationships between them. Okay? So a graph is just essentially a set of vertices and edges. There are things, which are the vertices, and relationships between things, the edges. Now, sometimes you'll hear different terms for them. You'll hear me use interchangeably the term node and vertice. This is because I come from a networking background. And a lot of times when we're talking about graphs and networking, we just call them nodes because that's just useful to always use the same terminology. But the proper mathematical name is vertice. So let's go ahead and pull up the slides because there's some nice drawn examples, and I'll draw some, and I'll be doing plenty of drawing myself. Okay, so Kaufman. All right. So this chapter we are going to. So today it's going to be a lot about terminology and learning about the different types of graphs. In other words, the directed versus undirected graphs and the weighted versus unweighted graphs. We're going to basically look at the different ways you can implement graphs. Then we're going to learn about the graph. And once we do that, we're going to start stepping into graph algorithms. So your first assignment will be learning how to use a graph library and doing a couple of very basic assignments on them. The first basic is, so you'll learn how to do breadth. So you're going to use the graph library to perform breadth first search and depth first search. And then after that, you'll do a more complicated algorithm called Dijkstra's algorithm, which isn't too hard to do by hand, but on the computer, you got to know what you're doing. You really have to understand what we're talking about. And then, and that's something that you need to do on weighted graphs. Dijkstra's is a shortest path algorithm, meaning it finds the shortest path from a node to all the other nodes. And then we're going to study what things we can do with graph algorithms, which is kind of like anything. So graphs are limited they're limited in a data. So trees are limited in the fact that you have only one parent. Trees are a type of graph. Graphs don't have parents or successors. We just say they have neighbors or adjacent nodes. Graphs overcome this whole. They're a much more, abstract kind of thing. So they were being studied a while ago. The most famous old graph problem is the bridges of Königsberg. Yeah, I apparently cannot type today. Okay, so the 7 bridges of Königsberg. Okay, and it was solved by it was unsolved, I suppose to say, or not by Leonhard Euler, who said basically you can't solve this problem. Okay, and the idea was, here's a bridge. This is the maps of Königsberg, and those green and the bridges are highlighted in green there. Okay. Let's see. More details. Can I get a bigger picture? No, I cannot. So zoom in. Okay. So, and it was essentially something that, children and then adults would also try to do, which is because, you don't have TV, so there isn't too much to entertain you. And the idea is that can you figure out a way to cross each bridge once and only once? Cross all 7 bridges, but cross each one once and only once. Sorry? Swim. Right. Right. No, you got to stay on land. People are like, oh, how clever of you. But no, you want to. And besides, 1700s, you don't want to go swimming in that water. Oh. Okay. And, it was like people would claim there's a solution, like somebody's cousin's brother's uncle, solved it. But nobody could. Right. And then it took Euler, and Euler was presented with this problem, and he's like, well, actually, you can't solve this, and I can prove it. And essentially he showed that basically by what he did is that, it became he pointed out the choice of route to each landmass is relevant. The only thing that's important is the sequence of bridges you cross. So he made it more abstract, right? You turn it into this thing, right, where you've got the land masses, and then you can turn it into this thing, a graph, right? Notice this dot over here. It's got 5 coming out of it. That maps perfectly to this island over here, which has 5 bridges coming out of it. So it just simply said you have these nodes, And here you have like a node. This has two connections, right? Now, when we're with the graphs we're dealing with simple graph. This is what we call complex graph, where nodes can have more than one edges between them. They get one or more relationships. The graphs we're going to be dealing with are simple, where they can have either a relationship or they don't have a relationship, right? So, and he showed that basically that he found an equation essentially that showed that you can't actually cross all the bridges, and abstracted it out. It was finally solved, I think, by the fact that a couple of them were blown up during World War II, and then two more of them were just torn down for a highway. So now the problem can be solved using just the remaining bridges. So that's great. Those destroyed are highlighted in red. Those remaining are green. So 1, 2, 3, 4, or let's see, or 1, 2. Can you solve it? It's just those with those wiped out.
It's just a circle.
It's just a circle. 1, 2, 3, 4, 5. Yep, you can solve it. Go here, go here, go here, go here, and go here, and end up in the middle. You've crossed all 5 bridges, right? You can solve it now that that 2 of the bridges have been completely destroyed. So I guess thanks World War II. Sure. So anyway, this is this was a famous graph problem. But they've been studied for a while, long before we had to think about data structures. So a lot of the algorithms, they existed before data structures or object-oriented programming. So graph algorithms are important for like any kind of large communication network, like the internet, right? Or satellites, or figuring out where you want to put components on a computer chip, road mapping, figuring out airline routes. Also, they're used for like figuring out whether or not you can take a course, right? Do you meet the prerequisites for the course? So figuring out whether to tell the student that they can't take this course that they really want to take, that's a graph problem, So the first thing we need to do is, of course, just nail down our terminology. Like I said, graphs are sets of vertices or nodes and edges, the relationships between them. And both the sets can be empty, but you can't you can't have any edges if there's no vertices, right? You have to have things to have a relationship to. So visual representations of graphs are useful for us because we're humans, right? But and we typically represent it by basically giving each node a label and then drawing lines between each node for the edges. So here we have the mathematical representation, which is A, B, C, D, and E for the vertices, and the edges we describe as having an edge between A and B, and A and D, right? So A and B and A and D. Notice that we don't label them; we just simply draw between the appropriate edges. An edge between C and E, and an edge between D and E. Okay. Each edge is connected by the two vertices that. So each edges would need vertices to exist. In other words, each edge is defined by the two vertices it connects. And if an edge exists between vertices x and y, we say there's a path from x to y, and a path from y to x. There's also a path from B to C, right? You can go from B to A to D to E to C, right? So if you can basically walk along the graph to them, there's a path. Okay, the vertical layout. So the way you lay these things out, it's not really relevant. You don't need. So here we're using numbers instead of letters for each of the nodes, and here we have the mathematical representation, the nodes 0 through 6. Notice that these both have 0 through 6, and notice the one what node 0 is connected to. It's connected to 0 is connected to 1, 2, 5, and 6. And over here we see that's connected to 1, 2, 5, and 6. 1, 2, 5, and 6. From our standpoint, these are the exact same graphs, right? Because they're just simply the same relationships, just laid out differently. So the physical layout for graphs doesn't matter, okay? The way graphs physically look on a page, that doesn't matter except aesthetically, but for aesthetics. There are kind of definitions that do matter, like with terms of the layout. Like a graph is planar if you can draw the graph without any of the edges crossing one another, like physically overlapping each other. And you know, there's properties to be planar, but obviously if you want to draw it, we could draw this with things crossing. But the question is whether it's planar is whether it can be drawn without things crossing. But again, so you can draw graphs however you want, is the point. So, and these are what we call undirected graphs, because if there's an edge between 0 and 1, that means the edge goes from 1 to 0 as well. The other type of graph, as we mentioned, was undirected. So that means that basically if there's a path from A to B does not necessarily guarantee there's a path from B to A. So here we have, in this graph, we have an edge that goes from A to B, an edge that goes from B to A, E to A, but not A to E. This is called a directed graph, or sometimes a digraph for short. And then if it's undirected, we just simply call it a graph, right? Or an undirected graph, right? Undirected is the default assumption. Directed is, and we draw, and it's essentially a directed edge is a one-way street. It's a one-way relationship. It only travels in one direction. So we represent it as lines with an arrow, so it goes from A to B and then B to E, okay? And then we represent them in edges as source destination. So we have an edge. So this is an edge A to B, B to A, B to E, right? B to E, but no E to B, D to A, E to A, E to C, and E to D. And actually, this list of edges, interestingly enough, is enough to define the graph. We don't actually have to list the vertices for this. If we just go off the edges and say, oh, okay, so there's an edge from A to B, so I'll draw A and B, because in order for an edge to exist between A and B, there has to be, something drawn there. And then there's an edge from B to A, okay? And then there's an edge from B to E. And then there's an edge from D to A, right? And then an edge from E to A, and E to C, and E to D, right? I can just use the edges to draw my graph in most cases. Some cases you can't, where might be an edge, a node all by itself that doesn't have any edges going to it. So we have edges and we have directed edges. We have graphs, and we have directed graphs, undirected graphs, and then graphs can also be weighted or unweighted. That means whether or not there's a number associated with it. It doesn't have to be a number, but for most problems it is. Like, I haven't really seen one that isn't a number, and you'd want to turn it into a number for most of the algorithms we use anyway. So edges in graphs, they can have weights, and if it has weights, it's a weighted graph. So this is kind of a graph that shows distances between cities, right? About 320 between Philadelphia and Pittsburgh, 180 between Pittsburgh and Columbus, 180 between Columbus and Indianapolis, and 180 between Indianapolis and Chicago. So, so we talked about paths, and that's kind of an intuitive thing. If you can get from one node to another node, there's a path between them. So a vertex is adjacent to another vertex if you have an edge that connects them, right? So Philadelphia and Pittsburgh in this graph are adjacent to one another. You might not consider them adjacent. You might say that Philadelphia is adjacent to Harrisburg, right? But in this definition, right, because Harrisburg isn't listed on there, we're just concerned with Pittsburgh and Philadelphia. They're adjacent there. Indianapolis is adjacent to Columbus. In this one, A is adjacent to D because you can get from A to A. You can get to A from D. But D is not adjacent to A because you can't get to A. You can't get to D from A. That is a definition that I will never test you on, by But you're adjacent if there's another edge to it from another vertex. So a path is a sequence of adjacent vertices. Like here's a path from Philadelphia to Chicago. I actually drove that not too long ago. It's a long drive. In this simple path, the vertices and edges in a simple path, that's it. Basically, the vertices and edges are all different except for the starting and end point. They can be the same, right? Here, the starting point and the end point are different. But if you think about if you go for a jog, right? If you have a path for jogging, you're probably not going to jog along the same street more than once, right? Right? If you're jogging, you're making some kind of circuit, right? And you're going to want to start at your house, and then you're going to want to end at your place if you're jogging, right? Because your stuff's there. But ideally, you're not going to want to go over the same place twice because otherwise you're going to be repeating stuff you've seen, and that's boring. So that would be a simple path. Specifically, so this is not a simple path because we're repeating stuff for God knows how long. A cycle is a simple path. So that jogging thing I just described is a cycle. It's a simple path that starts and ends at the same point. So here we have a cycle that starts and ends at Pittsburgh. If you're and you need at least 3 nodes to be a cycle. So 2 adjacent nodes isn't enough to be a cycle. You need to be able to go from A to B, B to C, and C to A to be a cycle. Okay. So now this graph is what we call connected, meaning that there's a path from every other vertex to any other vertex. And pretty much all the major cities in the United States would form a connected graph because you can drive from any major city in the mainland United States, the contiguous 48 to any other, thanks to the wonders of the interstate highway system, right? You can drive from any city to any other city. Okay. So this is a connected graph. This is a connected graph. But if we remove the edge 4 to 6, this will be an unconnected graph. Okay? Think of it like maybe these islands of Hawaii, right? Where basically you can drive along all the major, between all the places you want on an island, but you can't really drive from one island to another island, right? Now these graphs are still made up of connected components, right? Which are kind of like mini graphs inside of the graph, right? So this is a graph, the valid graph. It just happens to be that you can't, that it's made up of 2, it's unconnected. You can't get from everywhere to everywhere else. A single vertex just by itself is also considered a connected component. It's a tiny little island all by itself. Trees are graphs. Any graph that is connected, so any graph that's connected and has no cycles, you can turn it into a tree by just grabbing any one of the nodes and just kind of dangling it from that node and making that node the root. So here we grab D and we just kind of arrange it vertically. Right? Not necessarily a binary search tree, just a tree. So things that we can use graphs for is like to determine whether everything in the network is connected to each other. Can you route from all locations to any other locations? Map out all the course prerequisites. Find the shortest route from one city to another. So the least cost or the shortest path in a way to graph. So that's actually a very solved problem, and there's a lot of different ways to do it. There's Dijkstra's, there's Dominant's Ford, there's other algorithms that people have their names to. But it turns out that while finding the shortest path is something pretty easy to solve. Finding the longest path, on the other hand, the largest path, is actually a really hard problem. It's an NP complete problem. It's not one that's easily solvable. Let's see, is there a mic in here? So there is. Hello? Sorry, just give me 1 second. I was hoping there was a mic. what does it connect to? Oh, let's see. That just sounds like headphones, but nope, don't need that. Don't need this. I'm sure they love me for doing this. Yeah, it's a Bible. I don't need that. I suppose I'm just going to suffer. And blue books, because you really need blue books. Okay. So whatever. I'll just have to suffer. All right. So anyway, finding the longest path is a NP-complete problem, which means that it's really hard. Specifically, NP stands for non-deterministic polynomial, which means that basically that on a regular computer you can't really solve it in polynomial time, but we can check the answer in polynomial time. So if you give me a solution, I can check it relatively quickly. But asking me to solve it, there's really no better way than me to solve it than to actually compute every single possible path and find out which one's the largest path. Another one is the traveling salesperson, which is that basically given a special type of graph called a clique. So let me draw that. A clique is, again, a special type of graph where basically you can go from any one node to any other node. So this is a 3 clique, right? We can go from any node here to any other node. A 4 clique, looks like this. So adding a 4th node, we would have an edge here, an edge here, an edge here, and adding a 5th node, we would connect to all those. So the traveling salesperson is given this fully connected graph, this clique. Find the shortest route that travels to all the nodes. And that one's an NP-complete problem too. All right, so, okay, now that I've got these vertices and edges and they can be connected, unconnected, how in the world do I implement them? And the answer is that we're going to talk about the different ways they're implemented, but we're not going to use their stuff, right? Because they really do it with just integers, and I think that's silly. Instead, what we're going to do is that we are going to use libraries that people have written for us. So if you've decided to use Python for this, you're on your own for the most part, except for the fact that people have are wonderful and they write documentation for everything. So let's see, networkx. So you'll want to use this if you're using Python. It's called networkx. Look, graph. Isn't that nice? It's just like, and you can like pull it and stuff. That's cool. All right. You want to download it. You can download it using pip. You can also download it just, as a zip. And they have a PDF for documentation, which has 666 pages, apparently. You can also look at the HTML pages. And generally, all you'll need to read is the installation and the tutorial, which will tell you how to do it. Once you install it, you'll be able to import it, and that will be pretty cool. And you can pretty much use anything you want. And you can use anything you want as edges and anything you want as vertices. So if you're into Python, you can use that. I don't know for other languages. For Java, we're going to use something called Jung, or Jung, named after Carl Jung, I think. But it's the Java Universal Network and Graph Framework. And it hasn't been updated in like 7 years, but whatever. I think now somebody did fork it on GitHub. And you're welcome to try using that, and they've updated it. Jung website. So they've actually updated Jung. So they've updated that one, because that's the way open source projects work. You can update stuff and once it stops being maintained. So it's an API. Essentially, that means it's a bunch of, it's a library. So here's what we are going to do. We are going to, let me just open up IntelliJ and delete my project that I did from last night because I want to do this basically from scratch for you guys. And then, let's see, let me just go and get NetBeans as well. I think though that because I'm using Java 9, NetBeans might not be able to install that on my computer. So let's see. Yeah, I can't use it on my computer because I've got Java 9 on my computer. Whatever. So NetBeans, that's going to be a thing you're going to have to figure out on your own. But it's not too bad. You just add an external library for it. All right. So let's see. Close project. Graphs. Okay. And Andrew graphs. Delete that. Awesome. So now we're starting from scratch essentially. So the way we so first thing, there's essentially three things you'll want to read here. Overview, the download, documentation. Let's see, are the examples anything useful? Is the wiki useful at all? Wiki can't be found. The demos, those are applets, but your computer probably doesn't run applets anymore. So really all we care about is the download page and the documentation page. So first, let's go and download Young. You're going to want to do this regardless of what you're using. Download them here as of and it says basically that they've updated the project here. So if you want to use the newer version, you can. That's fine. Or you can download the older version, which is what I've got. Let's go ahead and see what's in the newer version and see if I can't get that working. So unzip it. Download it, unzip it. Did I download the source file? Yeah, seems so. Let's see. Do they have a README? Read the README if they have got one. So latest release tells you. So yeah, I'm going to use the old one because it just simply has jars files in it. So I'm going to extract the file. And what you'll see is that when you extract the library, it has a bunch of these what are called jar files, and you'll see that they have the Java icon, right? And then there are a bunch of things that end with .jar. So anybody know what a jar is?
I'm still trying to figure that out.
J, Java, R, archive, Java archive. It's a Java archive. Actually, all it is really a zip file. It just has it's literally a zip file with a different 3-letter extension, just to tell people that it's got a bunch of Java classes in it. So you can open it up with a program, archive, and it's a bunch of packages. It's a package edu.ics.jung, algorithms, and then it's got a bunch of classes inside of them. So, however, we've got it downloaded. And then let's go ahead and how do we get them into our IDE? Well, the easiest way I found to do for pretty much everything is Control-A, Control-C to copy things over. So let's go ahead and make a new project called Graphs. Okay, and what I do for here, what I do is to get them into my project. Just like you have a file, just like you would need a file to live on the top level of your project to be read, you need these things to be on the top level to be used. So I Control-V them into my graphs folder. Okay? Then what I want to do is I want to select all the jar files that I just grabbed. Okay? Right-click. And here I want to, let's see. I don't want to add to favorites, but add as a library. In other words, I'm now telling Java, now telling my IDE, not Java, I'm telling IntelliJ that I want to use these things. And I just want to use those together. So now I'll be able to build a program using them. So now, just example, graph, example. Now my library knows they exist. Okay? So if I go to graph example, void main, I can do graph. And then it says, are you asking about the graph interface from edu.uci.ics.jung.graph? are you asking for that one? And I'm like, yes, that's the one I'm talking about because, right? And you know it's the one you want because it's from Young, right? And so now I can go through and work through all the examples that they have, which I'll get to in a bit. Okay, what if you're using something like Eclipse? Okay, well, let's go ahead and open up Eclipse. And pretty much the only reason I have Eclipse right still is because I want to show people how this works. Let's see, and let's go ahead and see if there's a NetBeans portable. Downloads. So it's still loading. Yeah, can I download? Can I download a? Yeah, so it's not on. Here, so it says I can't use Java 9 with it, but I think the development version does use Java 9. So I'll download the latest development version of it, and hopefully that will run. Okay, so save, because a lot of you do use, I know a lot of you still use NetBeans. So anyway, in Eclipse, let's create a new project. New Java project, graph example. Same kind of thing applies here. Top level directory of your project. I copy in all the files all the jar files. And then for Java, in order to recognize that there are files that you want to use in your project, you select them all. So you can do that by, control clicking on them individually, or click on one, hold shift, right click on the ones you want to go through, because apparently people don't know these keyboard shortcuts. But you have to learn them somehow. I don't know how you learn them. There's not like a class on keyboard shortcuts. So, and then we just go build path. So select build path, add to build path. And now it said it puts them in a folder called reference libraries. So now if I go over here and create graph, public static void main string args, right? Now I can do graph G, or sorry, I want to call it graph refactor, rename to graph x, finish, graph G. So it's saying what graph do I want to use, so I click on it, and it says, import graph from edu.uci. So that's, once you see that, you've got it loaded up. Okay. So NetBeans is a bit different. So I'm installing the latest version of NetBeans. Like, it might crash on me. Oh, it says, oh, come on, I have an SDK. Ugh. So, okay, I guess I can't show NetBeans off. I might make a video for that later at some point, but whatever. But with NetBeans, it's actually fairly straightforward. How to add external library jars to NetBeans. How to add a jar in NetBeans. Hey, Stack Overflow. Right? So, compile time libraries, which is needed to compile your application. Runtime, they need to be included in your library management. So right-click on libraries in the project list, and then click Add. Right? And that will basically, and then it will bring up a file dialog, if I recall correctly, where you can say where your libraries are located on your computer. And so long as you don't move them to a different location or delete them, NetBeans will be able to use them. Okay. Let's see what that. And then there's some videos, which probably, hopefully, let's see. Yeah, you can probably, yep, those look, yep, add jar folder, and then you'll just simply route to it. It's a pretty painless process, but it's one thing that you have to make sure you do correctly. Okay, so do you want to exit Eclipse? Yes, I want to exit Eclipse. Okay, so that's what you'll want to do basically. So getting this part done is a fairly easy part of your homework, but it's unusual. You won't have done it before probably. For again, if you're running Python, you'll want to do something like you want to use pip or pip3 to install it on your computer, and that's you just need to run this command and it will work. I think I already have it installed, so it's going to yell at me. Yep, it's already satisfying, and then I can tell it's telling me I've already have it and I can upgrade it. And then once I can use it if I go import networkx as nx, and that means I can refer to the library as nx, and then I can use it. So that's cool. So again, really, I'm kind of agnostic. The algorithms are what's more important here. Okay, so before I get into like how to build things, I want to talk about how are they actually going to be represented, right? Because there's two primary ways to represent graphs based on whether they're sparse or dense graphs. Sparse graphs meaning there's a kind of a one-to-one relationship between the number of nodes and the number of edges. So basically, if there's one node, one edge, basically per pair of nodes, that's a pretty sparse graph. A dense graph is, it's the opposite. You have a lot of edges. And remember, you can have, if there's n edges, you can, then there's, if you have v vertices, right? Each vertice can have a connection to each of the other v minus 1 vertices. It's also technically possible for a vertice to have a connection with itself. Like for instance, if your edges are representing energy to move between states, right? It's more expensive to change your state, and if you keep your current state, you'll lose just a little bit of energy. So that kind of represents that. So this is the total possible number of edges in a simple graph, v squared. So there's two different types of ways we can represent graphs. You can represent them as adjacency lists or adjacency matrices. Okay, and that just depends on whether they're sparse or not. And so when you're using Jung, you'll see stuff like sparse graph and not sparse graph. So and if it's sparse, it's going to use the adjacency list. Otherwise, it'll use an adjacency matrix. So and I only want to bring that part up first because now that I'm going to start actually going through the Jung demo, I want you to actually be able to see that. So I'm going to stop this recording and just immediately restart it so I can post it to the other class too because they didn't get this part.